Hi, it's Mr. T here. In today's video, we're going to look at the reactions of alcohols that we need to know for a more advanced organic chemistry course, and specific the level 3 NCA chemistry course. Look, I'm an experienced chemistry teacher. I've taught chemistry for over 22 years at high school, and this video should give you a really good start to mastering this topic. So, reactions of alcohols. So when we look at alcohols, it's important at this level that we're able to distinguish them between primary, secondary and tertiary alcohols. And in the reaction scheme we're going to start to look at today, we're going to look at, for a start, two different types of oxidation reactions to do with alcohols that produce aldehydes and ketones. We're going to look at the substitution reaction with halogens that produces a haloalkane, and we are then going to look at this elimination reaction that happens with concentrated H2SO4. Okay, so right, let's have a look. So the first type of reaction we're going to look at is oxidation reaction, and we're going to look at oxidation reaction of primary alcohols. Now we have two oxidation reagents we use. We use acidified permanganate, which is MnO4 minus with a We/H+. H+ means there's acid added to permanganate. Or we use acidified dichromate, which is Cr2O72 minus/H+. Now, one thing I want you to notice here is that when we oxidize an alcohol, if we put the reagent and the sample into, let's say, a volumetric flask, or we put it into a round bottom flask and we heat it, we get a reaction that happens, and the alcohol gets oxidized to an aldehyde. That's what the primary alcohol changes to an aldehyde. However, if I keep this mixture, if I keep heating it, it will continue to react with the oxidizing agents that are still around, and it will turn the mixture all the way into a carboxylic acid. So it's kind of like a two-step process. If I want to stop this process halfway along the way, I've got to get the aldehyde out before it has the opportunity to react with the carboxylic acid. And I'll go through the details on how we do that when we look at the reactions of aldehydes. But knowing for the moment, an alcohol, when we add an oxidizing agent, goes to an aldehyde. If we add dichromate, we get exactly the same reaction, okay, but we're just using a different oxidizing agent. We are changing the primary alcohol into an aldehyde. And remember, if we keep it in the solution, it will continue to react and produce a carboxylic acid. So that's what happens to a primary alcohol. We produce an aldehyde from a primary alcohol, and then the aldehyde can go on further and react with carboxylic acid if we don't stop it reacting. Okay, so what happens to a secondary alcohol? Well, a secondary alcohol doesn't have the OH on the end of the molecule, so it's not going to be able to produce an aldehyde. So what we see here is, now the alcohol is found on a carbon that is not at the end, we're going to produce the double bond in the middle, and therefore this is going to produce a ketone. The other thing we can notice here is this ketone cannot react any further. We can't add another OH, we can't add another oxygen bond, because there are no hydrogens to remove from this carbon. There are no more bonds that we can create to new substituents. The only way to add more oxygens to this carbon is to totally break this molecule up, and that would destroy this molecule, and that wouldn't be an organic reaction anymore, that would be a combustion reaction. So remember here, we could also use the dichromate Cr2O72 minus that's been acidified, and it would give us exactly the same products. Okay, if I tried a tertiary alcohol, and notice this one at the bottom, the OH is attached to the carbon, there is no way that I can make another bond to the oxygen without destroying this molecule, because there are no hydrogens that we can easily remove. In this case, oxidation using permanganate or dichromate does not occur when I have a tertiary alcohol. So this is really good to know if I want to distinguish between a tertiary alcohol and a secondary alcohol, or a tertiary alcohol and a primary alcohol. I can just try and oxidize them with permanganate or acidified permanganate or acidified dichromate. If it does oxidize, it's going to be the primary or secondary, and if it doesn't, then it's obviously going to be the tertiary. Okay, so let's have another type of reaction here, substitution reaction. Now, so we can either add phosphorus pentachloride, phosphorus trichloride, or thionyl chloride to an alcohol to produce a haloalkane. And the haloalkane in this case is going to be a chloroalkane, because we're actually adding chlorines here. Now, there's a reason that we like to add thionyl chloride to this solution, and the reason that we do this, we know that we go from an alcohol here to a haloalkane, is that when we produce PCl5, when we use the reagent PCl5, we're left with these two extra non-organic products floating around in our solution. This not sure what the name of this is, but these are both floating around here, and then we've got this phosphoric acid here floating around in the solution. When I use this thionyl chloride, notice the sulfur dioxide and the hydrochloric acid are gases. So I've got an organic solution with gases in here. So as soon as this happens, it's also producing sulfur dioxide and hydrochloric acid gas, but those gases, what they do is they bubble off, and you can collect the gases away and you're left with the pure product. If I use the PCl5, I would still have these this POCl3 sort of mixing around with the haloalkane, and I would have to try and get it away somewhere. So it's kind of messy. So we love to use this thionyl chloride when we produce a haloalkane. Okay, so the other way we can produce a haloalkane from substitution is we can use a halogen attached to a hydrogen. Now, the problem with a halogen attached to the hydrogen is the type of organic reaction it undergoes, and unfortunately they only readily undergo these type of reactions with tertiary or secondary alcohols. So if you have your OH attached to a tertiary or a secondary position, this is a good way to add a halogen. So I can add my bromine here, or I could substitute if it was an HCl. If I do substitute with an HCl to produce my haloalkane, this is called Lucas reagent. So we can use, instead of hydrogen bromide here, if I used HCl, Lucas reagent would react very quickly with this alcohol here to substitute the hydroxyl group with the chlorine. And when it did react, this new haloalkane would no longer dissolve in the water like the alcohol did, and so you would get a cloudy solution. Okay, so you get a cloudy solution because we've got two immiscible solutions here. They don't dissolve in each other. If I had just a secondary, if this OH was joined, say, just here, and it was a secondary alcohol, we would have to heat it for it to react, and it would go cloudy in about 30 minutes. If we had a primary alcohol, it would not react. Hence, we use Lucas reagent when we want to confirm that we have a tertiary alcohol, because this type of reaction will happen straight away. So those are the substitution reactions of alcohol, and we've looked at the oxidation reactions of alcohol. The next type of reaction is an elimination reaction. So alcohols, if we add concentrated sulfuric acid, which has a huge affinity for water, so it will rip water just about out of anything. So if we add it to this molecule here, it's going to take the hydroxyl group and an adjacent hydrogen, so it gets its molecule of water. Okay, so that's what it's going to do, and once it's ripped these two away, these bonds reform here and we get this double bond form. So this is our elimination reaction. So we turn an alcohol using concentrated sulfuric acid into an alkene. Now this is a useful reaction. I'll tell you why it's useful. The reason why is we can use it to change the position of hydroxyl groups. Now, the way that we do that is we actually can add our concentrated sulfuric acid and make our alkene, right? So we take this hydroxyl group, okay, that is attached to the number 1 carbon, and then we turn it into an alkene that has the double bond on the first carbon, because that's the only place that the double bond can form when I take away this OH and an adjacent H. However, when I then go back and add water again, and I add water by putting it in an acidic mixture, so H2O/H+, using Markovnikov's rule, the majority of the reaction occurs, the reactions occur when the OH, the hydrogen attaches to the carbon that has the most hydrogens. So you can see here that the hydrogen attaches to the right carbon and the OH attaches to the left carbon. So by doing these 2 different reactions, this elimination reaction and then this addition reaction, you can see what we've essentially done is we have changed the position of the OH from being on the first carbon to the second carbon. Now this is really important when I want to manufacture specific organic molecules that have specific properties. And if the organic molecule I want to produce has the functional group on the second carbon instead of the first, I can do this elimination then addition reaction. Okay, so when we do these reactions, we have to be conscious of Zaitchev's rule. Okay, and Zaitchev's rule is a kind of the opposite of Markovnikov's rule. And the rule is that when we do remove this OH, we have to decide which adjacent hydrogen we're going to remove. And the basic rule is that the major product will be the hydrogen that has the least hydrogens will be the one that loses its hydrogens. And he said that the poor gets poorer. So we look at each adjacent carbon, we count how many hydrogens they have. This one has 3, this one has 2. So in this case, we would take away the OH and this one here that's poorer. So we'd take away these substituents here and we'd form the double bond here the majority of the time. So the major product here is the one where it's in the middle, and the minor product would be when the OH and the H on the right is taken away. That's Zaitchev's rule, okay? And that's the rule about when we have an elimination, which side the double bond forms on. The poor get poorer. The carbon with the least hydrogens is the one that loses the hydrogen. Yellow one, our rich one, red one, our poor one. Okay, so what you want to do now is pause this video and write down this reaction scheme. Notice on the left, I have a primary alcohol, and on the right, I have a secondary alcohol. You want to see if you can write the products of these 4 different reactions. And once you start it again, you'll see the answers as I put them up. So the bottom one is an elimination reaction. It only has one place to go, so we don't have to use Zaitchev's rule. This one here is an oxidation reaction. We see that it goes to an aldehyde. You might know that if we continue to react it, it will go to a carboxylic acid, but let's just focus on the first product that it goes to. And then we had the substitution reaction here by adding PCl5. The chlorine is substituting the OH there. And the last one here is we're oxidizing this ketone, and we produce, oxidizing the secondary alcohol, and we produce this ketone. And so those are the answers to these 4 reactions. How did you go with that? Hopefully this video was helpful in getting you up to speed and on your alcohol reactions. Please share the video, make sure that you subscribe and like, and look out for the next video that's going to be on haloalkanes.